A Russian is the first to walk in space, but this is the first American. It's 1965, and a dream is coming true. It begins long ago in China with the invention of the rocket. After setbacks, it's carried forward by physicist Robert Goddard. In 1926, he launches a liquid fuel rocket, a prototype for space. World War II, and the Germans developed powerful military rockets. Their chief designer, Wernher von Braun, is lured to America. But the Soviet Union is first into space. Sputnik, an artificial satellite, curves into orbit. It's October 1957. A month later, a Soviet dog is in space. America responds with flopniks. Success, though, in 1961 with Ham the chimp. He takes a round trip into space. His heart rate rockets, but Ham quickly returns to normal, and he returns, unlike the dog. Meanwhile, the Soviets are secretly ready for the big one. Former test pilot Yuri Gagarin couldn't be cooler. On April the 12th, 1961, Gagarin blasts into history. His rocket, a modified ballistic missile. The first Soviet cosmonaut is in orbit. And a hero returns. Their space program seems unstoppable. Cotton mill worker Valentina Tereshkova becomes the first woman in space. Alexei Leonov is the first to venture from his craft and walk in space. America's President Kennedy picks up the challenge.
To achieving the goal, before this decade is out, of landing a man on the moon and returning him safely to the Earth.
Phase 1, the Mercury Project. 7 astronauts, including John Glenn. Al Shepard is first to squeeze into a Mercury capsule for a suborbital hop. But it's Glenn who is first into space aboard Friendship 7.
Roger, 0G, and I feel fine.
10 months after Gagarin, Glenn is in Earth orbit. The mission goes well. Glenn relaxes, he even snacks. He completes 3 Earth orbits, then a warning that the heat shield is loose. The craft could burn up on re-entering the atmosphere. It's a rocky ride. But Glenn comes through. The Moon Program, Phase 2. The Gemini Project. 1965, Ed White takes America's first spacewalk. In Earth orbit, practice for lunar orbit. Astronauts have their eyes on the moon. The dream is alive. 2 Gemini craft, the first rendezvous in space. And the first docking, Gemini and a rocket. Suddenly Gemini spins. But they regain control. The astronauts make it back. Phase 3, Apollo. But disaster as 3 astronauts perish during launch pad training. fire consumes their capsule. Saturn, the great rocket developed by von Braun, the thrust of Apollo. 1968, and Apollo 8 loops right around the moon. Triumph in place of tears. Early 1969, a lunar spacesuit is tested. So too the lunar landing module. It rehearses with the command vehicle of Apollo 9. Apollo 11, Neil Armstrong and Buzz Aldrin are the ones there to land on the moon. Michael Collins stays in the command module as the lander Eagle begins its descent. Armstrong has studied the maps. He knows every crater, every rock. It's vital, for only seconds of fuel remain. He spots a landing site.
20 feet down, 2.5. Picking up some dust. 4 forward, drift into the right a little. Down a half. 30 seconds.
Eagle makes a perfect touchdown.
Contact light. We copy you down, Eagle.
The realization of a dream. July the 20th, 1969, the decade has still 5 months to run. America is on the moon. Eagle blasts off after just 21 hours, 36 minutes on the surface. Loaded with samples, it closes with the command vehicle waiting in lunar orbit. The two craft edge carefully toward a docking. The return to Earth takes 3 days. (1970) ground control.
Houston, we've had a problem.
An explosion on Apollo 13. The world holds its breath. The craft is outward bound for the moon with astronauts Lovell, Swigert and Hayes. Mission controllers hunt for solutions. The service module is out of action. Aboard Apollo, it's plain survival. The crew abandons the command module, which is short of oxygen. They move into the tiny lunar lander, a life raft that carries them around the moon and limping back to Earth. With a panel blown, the service module is jettisoned. The crew is back in the command module, but re-entering Earth's atmosphere, Apollo 13 falls silent. Then, the crew is home, rescued from space. Altogether, there are 6 moon landings. The last, Apollo 17, is the first to carry a scientist, Jack Schmitt. He gets around in a lunar rover. But with the Soviets beaten to the moon, America loses interest. Moon flights are cancelled. In 1975, one last mission for Apollo's Saturn rocket. At the same time, a Soviet rocket blasts off. The craft link up in Earth orbit. Astronaut meets cosmonaut, and there's a new dream. Our expeditions into space are now an international affair. The delightful weightlessness of space. The tug of planet Earth. Gravity draws us down. Whatever tricks we play. In Earth orbit, we may be weightless, but gravity still pulls. These astronauts are hurtling around Earth at over 27,000 kilometers an hour. They're in free fall. So are these. Velocity keeps their craft in orbit. Too little, and they'll plunge to Earth. Velocity counters gravity. With insufficient launch velocity, a rocket fails to reach orbit. With greater propulsion, at over 27,000 kilometers an hour, success. But to escape Earth's gravity altogether needs a thrust of over 40,000 kilometers an hour. The Apollo missions to the Moon have achieved that. But this is 1981, a new, more economic age, and America's space shuttle. This craft doesn't need the expensive oomph of a rocket to the Moon. Shuttle's limit is Earth orbit. Shuttle is reusable. It launches as a rocket, orbits as a space station, re-enters as a chariot of fire. Thousands of ceramic tiles prevent burn-up in the upper atmosphere. Shuttle touches down as a glider. Shuttle is a qualified success. There's science and satellite launches. It even carries passengers. But in 1986, disaster. A seal ruptures. All aboard are killed. Shuttle doesn't fly again for 2.5 years. Meanwhile, the Soviet Union launches the space station Mir. 400 kilometers above Earth, Mir is in permanent orbit, a laboratory in the sky. It's serviced by ferries and a rotor of cosmonauts. With Shuttle back in business, there are link-ups, 9 dockings in the 1990s. For Russian and American, the shared experience of life in space. But what are the practicalities out there? Physical and mental fitness are essential. Selection is rigorous. This is life in a goldfish bowl. Plants grow in zero gravity. We needn't starve on a long mission. But what about the isolation and the need to get along? A round trip to Mars would take 18 months, a strain on the best of friends. The Russians are most experienced at long missions. One cosmonaut spent 438 days on Mir with no ill effects, but he was highly disciplined. Food is glutinous. Crumbs aren't allowed. Drinking is best through a straw. Appetites need stimulation. In space, hot air doesn't rise, so cooked food emits no aroma. The answer is a spicy menu. Sleeping is either in a bag strapped to the superstructure or in a cubicle for a little privacy. Mir orbits Earth every 90 minutes. Each day, 16 sunrises, 16 sunsets. But the crew sticks to a 24-hour clock. They start their day on Moscow time. Shuttle astronauts observe Houston time, and sometimes they run a shift system. A haircut, sir. Dampened trimmings are sucked away. In zero gravity, it's important to keep the air clean because nothing falls to the floor. Shuttle's suction toilet, officially the waste containment system. It cost $15 million. Mir's is more primitive, but it has two compared with Shuttle's one. Shampooing without water is a messy affair. There's no denying it can be smelly and noisy aboard these space vehicles, but crews quickly adjust. The Russians know most about selecting compatible crews. It's vital, especially for long-term stays on Mir.
They get soft and round and they don't make a sound. How they look remains a mystery.
And a party always helps boost morale.
I'm just thinking about dollies or rockets. Here I come again, my fantasy. Yeah, there I go again, my fantasy.
Whether for work or relaxation, Earth-watching is the joy of orbiting. Lightning beneath clouds. A Russian volcano. Forest fires. To prevent muscle wastage, exercise is crucial. Weightlessness isn't kind to the body. Muscles need something to push against. For the long-stay astronaut, a regular workout. Restrictive suits help. The wearer must work to move. Yet, however much they exercise, it still takes time to readjust to gravity back on Earth. This medic should know, Dr. Valery Polyakov, the Russian with the record for the longest single mission. Space is a hazardous vacuum, and space walks no stroll in the park. As it ages, Mir is dogged with trouble. There's fire, computer breakdown, and wayward solar arrays. External repairs are inevitable. But in 1997, a cargo module slams into the solar panels. No lives are lost, but Mir is blacked out and helpless for several hours, a serious setback for a very old station. Inside is a labyrinth, 5 modules added in stages since 1986 to the original base block. From here is generated a stream of scientific and technical research, and it shows that even in conditions like this, we could make it to Mars and back. Mir hints at things to come. Shuttle's role is different. It's a workhorse, a truck. It launches satellites and retrieves them for repair. Mapping, scientific experiments, commercial and military projects, Shuttle does them all. It looks idyllic, but working and living in space can be cumbersome and uncomfortable. The astronauts of Shuttle and the cosmonauts of Mir are the vanguard. One day, orbiting Earth and voyaging to the planets will be an option for us all. Future Shuttle. It takes off as a plane and it climbs. With sufficient height and the right speed, the pilot engages the rocket engine. Future Shuttle is in space, airport to orbit in one smooth hop. At the leisure wheel in the sky, it's Friday night. Future Shuttle is bang on time. Less than half an hour from takeoff, another party docks in and checks in for a weekend in space. A break to watch the heavens above and the Earth below. But this wheel is much more than a resort. It's a spaceport, a staging post for onward journeys to the moon. For the moon is colonized, and for economy's sake, it's more efficient to ferry cargo and personnel from Earth orbit than directly from Earth. In gravity 1/6 of hours, the transporter pod coasts to touchdown. This is no campsite, it's a metropolis. People live and work here, scientists, miners, gardeners. And beyond, on Mars, more colonies. Sealed, self-contained cities, modelled on the lunar bases and serviced by them. The moon and those spaceports are our stepping stones to the planets. That's the fantasy, this is the reality. ISS, the International Space Station. Assembled in Earth orbit around a Russian core, components are from America, Canada, Europe and Japan. Completion is scheduled for 2004. Shared by 13 nations, there are multinational crews and robots like this, an inspection ball. It monitors astronauts on spacewalks and checks the superstructure. Robot arms reposition modules. Every technology to maintain a structure the size of a football field. Initially, crews travel aloft on the old space shuttle, their lifeboat, Soyuz, the ferry used by the Russian space station Mir. 6 to a crew, lots of room with tours of duty just 90 days. Life on ISS is congenial, luxury compared with Mir. ISS is costing $100 billion. It takes over where Mir leaves off. The main objective, to test the long-term effects of living in space, vital if we're to get to Mars. And this is the new shuttle. Or at least a half-size prototype, the X-33. As construction of the International Space Station begins, so do test flights of the X-33. It's the forerunner of Venture Star, the shuttle that'll lift cargo 20 tons at a time to ISS, and it'll do it 10 times more cheaply than the old shuttle. And unlike the old shuttle, which dumped fuel tank and boosters on every flight, Venture Star is all-in-one, entirely reusable. From Earth orbit, a rocket to Mars. It's the late 21st century. Thanks to spaceports like ISS, the Red Planet is now colonized. The rocket shed, we close with this cold little world and its wispy atmosphere. Millions of kilometers from home, a city of human beings. But it's life in a bubble. Airtight corridors connect labs, factories, offices, homes. Outside with no spacesuit, you're dead. This city is self-sustaining. Biospheres produce food, energy is solar-powered, everything is recycled. Rocket packs are fun, but to be free of pressure suits, couldn't we turn Mars into Earth? Possibly, but it would take 100,000 years to induce a greenhouse effect and breathable air. To travel beyond Mars from the spaceport of the future, it would take up to 15 years to reach Pluto, the outermost planet. We're held back by our propulsion systems and limited fuel capacity. Solar energy can help, but on a voyage through the outer planets, it's a diminishing resource. The farther we journey, the dimmer is the light of the sun. But there's still the solar wind. We might gather it in vast sails and drift outward on electrified particles blown from the sun. Beyond the solar system, we need new propellants. Even at 1/10 the speed of light, it would take us 40 years to reach the nearest star. Ion or nuclear propulsion might give us the thrust, but for the time being, such voyages are science fiction. So where next? The Moon and Mars are first on our list, but what about Venus, Earth's hot sister? Might we colonize this hellish planet, disperse its clouds, reverse the runaway greenhouse effect? Maybe. The trick could be to seed the atmosphere with green algae. It feeds on the crushing carbon dioxide and releases oxygen. Water accumulates on the surface, the steamy climate cools, life takes hold. It's no quick fix. Only after hundreds of thousands of years does Venus start to look like Earth. And even if it's possible, is such planetary engineering desirable? Nature has a habit of reasserting itself. But how about this for planetary engineering? It's the idea of space guru Arthur C. Clarke. A tower rises 36,000 kilometers from the surface of Earth. An elevator to orbit. The tower is one of 4, reaching from the equator, the spokes of a gigantic wheel of which Earth is the hub. The need to measure time gives birth to astronomy. To know the date, to know the season, when to sow, when to prepare for winter. Today, skies like these are glimpsed only in remote locations, in places free of lights and pollution. In ancient times, everyone saw the sky and knew the sky. Like their ancestors, The hunter-gatherers of today use the sun to tell time. They know the motions of the heavens. True astronomy begins 6,000 years ago with the Babylonians. They chart celestial movements. They group stars into constellations. They imagine them as figures, the signs of the zodiac. The Babylonians observed wandering stars. We know them today as the 5 nearest planets. Simultaneously in China, astronomers map the cosmos, carefully recording such things as comets. In Egypt, the annual flooding of the Nile is signaled by the dawn rising of the star Sirius. Such cycles may be controlled by their gods, but the ancient Egyptians have good sense. They divide their astronomical calendar into 365 days. Much later in Central America, the Maya do the same, but their warrior god Venus offers an alternative calendar, 584 days. It's based on cyclical movements of the planet. As to the mechanics of the heavens, here's a Hindu view. Our world is supported by 4 elephants on the back of a turtle in an ocean of milk bounded by a serpent. Back in 300 BC, the Greeks are more scientific. They see a series of concentric crystal spheres in motion around the Earth. Riding each in its own sphere are the Sun, the Moon, and the 5 planets known at the time, those wandering stars. The background stars are set in the outermost sphere. Midsummer's Day 200 BC. The sun shines directly down a well at Aswan in Egypt. This is known to a librarian, Eratosthenes. He works several hundred kilometers to the north in Alexandria. There, at the same time, a pillar casts a shadow. He wonders why. The reason is the curvature of the Earth. As sunlight shines vertically down the well, it's at an angle in Alexandria. Simple geometry gives Eratosthenes the circumference of the planet and proof that the Earth isn't flat. The Greeks start to measure the sky. The first star map is compiled by the mathematician Hipparchus. He records the brightness of stars. And by observing eclipses, he tries to work out the relative distance to the moon and to the sun. Another Greek, Ptolemy, believes that the planets orbit the Earth. Such is his reputation that the mistaken notion persists for nearly 1,500 years. So how does Ptolemy account for the wanderings of the planets? While the rest of the stars move steadily across the sky, why do those wandering stars make little reverses? Ptolemy's explanation is epicycles, tiny circles described by the planets around their main orbital paths. He's wrong, but it fits his observations. Nicolaus Copernicus gets it right in the 16th century. He puts the sun at the center of our system. Brilliant work for a Polish churchman who does astronomy as a hobby. Copernicus has 5 planets in circular orbits of the Sun and the Moon in a circular orbit of Earth. The German Johannes Kepler refines the idea in the early 17th century. He has 3 laws. The first is that planets orbit the Sun in ellipses, not circles. The second is that orbital speed varies. It's slower farthest from the Sun, but speeds up close to. Kepler's third law is that the closer a planet is to the Sun, the faster it travels in its orbit. Observations by the Danish astronomer Tycho Brahe provide Kepler with the clue as to why planets seem to reverse. Here, blue Earth is overtaking red Mars. As it does, Mars appears to make a backwards loop. The Italian Galileo is the first to turn a telescope on the sky. It is the early 17th century and modern astronomy is underway. Craters are spied on the Moon, the Sun has spots, Jupiter moons. The Dutchman Christian Huygens discovers Saturn's biggest moon, and he correctly observes that the rings of Saturn are detached from the planet. This man identifies a gap in the rings. He's Giovanni Cassini, a French astronomer of Italian descent. His observation is in 1675 and, to this day, the gap bears his name, the Cassini division. The English genius Isaac Newton revolutionizes astronomy. He works out gravity, splits light, and shortens the telescope by using internal reflectors. A century later, William Herschel discovers the planet Uranus, and at Slough in England, he builds the biggest reflecting telescope in the world. His observations are prolific. They're published as catalogues, and he's the first to recognize that the stars of our galaxy form a flattened disk. In Ireland, the 3rd Earl of Ross builds an even larger telescope. Mounted between stone walls, it's completed in 1845 at Birr Castle. The Ross reflector glimpses galaxies beyond our own. Not fuzzy blobs, but galaxies with structure. This sketch, by Ross, is of a spiral. Here's the galaxy today. The 19th century yields two key tools. One is spectroscopy, the analysis of light to work out the nature of objects in space. The other is photography. This photo is the bright comet of 1882. In the 1920s, Edwin Hubble brilliantly employs both tools. At Mount Wilson, California, his great telescope records galaxy after galaxy, and the fact that they're all racing outward. Where optical instruments can't see, radio telescopes can. These dishes probe back in time toward the Big Bang, the seminal flash that sets Hubble's universe on its way. Ever more powerful telescopes penetrate deep into space. But the next discovery could be by an amateur. Pioneering isn't confined to professionals. Astronomy is the science of the people. Where navigators and trekkers once explored, we now chart our planet from space. Satellites in Earth orbit keep watch for us. In a rapidly changing world, technology sets the pace. Communication systems rely on satellites to speed information around the globe. Research satellites revolutionize our understanding of how the planet works. Meteosat, a weather satellite, launches to a height of 36,000 kilometers. Orbiting at Earth's rotational speed, it appears to hover above the equator. Meteosat shows us global weather patterns. Hot air rising at the equator moves north and south. Heavy cloud sweeps the temperate latitudes. Off the east coast of the United States, a hurricane. To the left, in Texas, storms generate tornadoes. Weather satellites track it all. Complex data is simplified by meteorologists for TV and newspapers. In a hurricane, timely forecasting enables us to take cover. From satellite, this Caribbean hurricane looks serene. At ground level, it's a different story. Winds of up to 300 kilometers an hour, transport dislocation, death and accident. In Bangladesh, the aftermath of a cyclone. We can't stop the cyclone, but we can control flooding. With satellite images, engineers pinpoint the best locations for barriers and dams. They'll save lives and land. Takeoff for Topex Poseidon. From orbit, this satellite systematically scans the globe. But it's only looking at the oceans. It measures sea level changes to an accuracy of 4.3 centimeters. This research is called remote sensing, and it's trawling a rich harvest. In 1 month, Topex Poseidon tells us more about the sea than have ships and sailors in 100 years. Oceans are key to our weather. Their upper 3 meters store the same amount of heat as the entire atmosphere. The exchange of that heat between ocean and atmosphere helps drive our weather. So by monitoring currents and temperatures, we can predict the weather. Ocean temperature is revealed by changes in sea level. If it's warm, the sea expands, swelling and rising. If it's cold, the ocean falls. In the Pacific, the curse of El Niño is revealed by satellite. When El Niño strikes, trade winds drop. Warm water, here in red, flows east instead of west. It surges towards South America, bringing rain. On the other side of the Pacific, Australia and Indonesia are left with cool waters and drought. Shipping benefits from an array of satellites. Vessels skirt fog banks and escape the highest seas thanks to data from weather satellites. Navigation satellites cover the world. By taking a fix from at least 3 of them, ships determine their positions to within 10 meters. And for skippers cracking a passage in ice, satellites spot the best way through. Had Titanic sailed in the satellite age, that iceberg would have been avoided. 1991, the eruption of Mount Pinatubo. Satellites measure the plume. Temperatures drop by 1 degree as volcanic dust girdles the Earth. Industrial emissions, which also affect the climate, are monitored from space. This satellite scans for atmospheric gases. It's sniffing for ozone. Ozone is our shield against dangerous radiation from the sun, ultraviolet. In the 1990s, ozone is depleted. Chemical emissions are blamed. Over the South Pole, the satellite reveals a great hole in the ozone layer. And it's been growing. Earth may be warming up. polar ice is slowly melting. Scientists can't agree why, but satellites keep watch. Is global warming Earth's natural thermostat? Or are we to blame? Either way, with just a small rise in sea level, this much of northwest Europe would drown. A tanker in trouble. A major oil spill, and the environmental consequences are appalling. Satellite images assist the cleanup. They show the size of the slick and where it's headed. And satellites seek out those who dump oil at sea. From Space Shuttle, burning oil wells, the environmental cost of the Gulf War. Kuwait before the war and after. Pictures from satellite. In Amazonia, a vast ecosystem is under threat. The rainforest is disappearing, home to half the species on Earth. Space Shuttle witnesses the fellings and the fires. We're destroying the forest that breathes out a quarter of all our oxygen. No one can ignore this evidence from orbit. Shuttle can only watch. This satellite works for better land use. It's called SPOT, a robotic eye on our cities. SPOT provides planners with a fresh perspective on urban and rural development. From different orbital positions, it images a development site. By combining the images, it produces a three-dimensional picture. Add computer enhancement, and the result is the ideal site for a new reservoir. Add radar to our eyes in the sky, and we penetrate volcanic dust. Here in the Philippines in 1991, radar shows us the black lava of Mount Pinatubo. And beneath the sands of the Sahara, radar uncovers ancient riverbeds. As these fields in false color testify, agriculture embraces the satellite. Crop by crop, season by season, a farm report from space. And there are health checks. Satellites alert growers to pests and blight. Dark patches spell trouble, the need to combat disease or bug. Like all armies, this one marches on its stomach, consuming everything in its path. But help is at hand. Locusts lay eggs in damp soil. From satellite, it shows yellow. In go the spray planes. Satellites. Patrollers of our planet. The robot explorers. Our envoys in the solar system. They reconnoiter where we want to go and where we'll never go. Liftoff for Mars, a destination top of our visiting list. Thrust clear of Earth's atmosphere on a Delta rocket, this American mission to the Red Planet is a robotic trailblazer. Stage by stage, like an insect emerging from a chrysalis, this planetary scout sheds nose cone and propulsion units. Soon, it flies free. As Earth recedes, a single wing unfurls. It's the solar panel, the energy source that powers the craft and its signals to mission control. For this is the Mars Surveyor Orbiter. As the name implies, its task is to slip into Martian orbit and survey the planet as never before. On the far side of Mars, a retro-rocket cuts Surveyor's speed. Orbital insertion is successful. But the orbit is elliptical, sweeping far into space. Surveyor needs a circular orbit. The key is the solar panel. At closest approach, the panel becomes an aerobrake in the Martian upper atmosphere. Only with a circular orbit can Surveyor properly survey. Swing by swing, aerobraking does the trick. Surveyor Orbiter is to study weather and terrain. A companion craft is to operate on the surface. It's a 10-year program. Launches are planned every 26 months. It means that when we arrive, there'll be a book, The Surveyor Guide to Mars. Voyager, most famous of the robots, the mission that shows us Jupiter. Twin craft Voyager 1 and Voyager 2 send us mouth-watering images. Launched in 1977, the probes careen through the gas giants. Saturn and its remarkable rings, ringlets in close-up, and this astonishing approach by Voyager 1. Saturn is the climax for Voyager 1. Mission complete, it exits the solar system. Voyager 2 heads for the outer giants. 5 years later, Uranus. And its craggy little moon, Miranda. This Miranda animation is from Voyager data. At this vast distance from the Sun, Voyager relies on nuclear rather than solar energy. 1989, Neptune, last of the giants. Voyager has been 12 years in space. Some time-lapse of the South Pole. An arc over the North Pole, and Voyager is done. An American triumph. Voyager 2 heads for interstellar space. Like its sibling Voyager 1, lost forever from the planets. Launching from Space Shuttle in 1990, this robot targets the Sun. But the route is via Jupiter. There, with gravity assist, the craft is catapulted toward the Sun. The mission is called Ulysses. The aim is to fly directly over the solar poles. Ulysses does it, and research moves on. In 1989, another robot launched from shuttle, Galileo. It's headed for Jupiter, but Galileo is short on thrust. Gravity assist is the answer, once round Venus and twice by Earth. It takes 6 long years, but it's worth it. This mission, to drop a probe into the merciless atmosphere of Jupiter, is only for a robot. At a command from Earth, the probe deploys. It's a descent into hell. The deeper, the denser, the hotter. There are terrible winds. But the probe keeps transmitting. Data is flashed to the mother craft for relay to Earth. The atmosphere is a poisonous soup, so dense that after an hour, the probe is crushed. Up above, Galileo slots into orbit. A gigantic ellipse, but slingshotting with a purpose. Each loop, a chance to photograph the 4 largest moons of Jupiter. Galileo's flybys yield dramatic pictures. July the 4th, 1997. America celebrates Independence Day with a night landing on Mars. It's a bouncing robot, the spunkiest vehicle ever to hit the red planet, Mars Pathfinder. It comes to rest on an ancient floodplain. Cocooned within, technology that beams us 16,500 images and more than 2.5 billion bits of information. But first, the deflation of the protective bags. Then, like a flower, Pathfinder spreads its petals. Sunrise, solar power, and contact with Earth. And so to work. Pathfinder has stereo cameras. A color image is produced by passing light from a lens through 3 filters. The process is duplicated with light from a second lens. So there are 2 images of the same scene. When merged, we see the Pathfinder landing site in 3D. A site worth investigating. Cue the rover. Although controlled from Earth, the rover can steer itself. Batteries last so well, the mission goes 4 times longer than planned. The only mishap, some bad driving. The first Martian fender bender. Elsewhere, there are worse mishaps. This Ariane rocket, carrying 4 robot probes, never makes it to orbit. Nor do these darts from Russia. Rocket failure means they never leave Earth orbit. They were supposed to analyze Martian soil and transmit the results to an orbiter. The great dishes that talk to our robots are the boon of space exploration. Through them, without leaving the security of planet Earth, we map and catalogue new worlds. Had Christopher Columbus been so lucky. The Pillars of Creation, one of the most spectacular pictures ever taken of the cosmos. It's part of the Eagle Nebula, where stars are born. A dying star in the Cat's Eye Nebula. Another in the Hourglass Nebula. Masterpieces from the Hubble Space Telescope. Seeing deep into space is to do with gathering light. The human eye does it by collecting light through a lens. This it brings to a focus on the retina at the back. But for a cosmic view, only a telescope gathers sufficient light. This telescope collects light with a mirror, bounces it to a smaller one, then to a third, and finally to a focal point at the side. But the clouds and dust of Earth's atmosphere impair the sight of even the most powerful telescope. The Keck telescope is halfway through the atmosphere at over 4,000 meters on Hawaii. But atmospheric turbulence causes images to shimmer. It's like looking through water. In the Canary Islands, the Herschel telescope is perched way above the clouds. So too the VLT, high in the Chilean Andes. The initials stand for the Very Large Telescope. 4 separate mirrors, each 8.2 meters wide, and each mounted on anti-distortion supports. They compensate for any flexing of the huge mirrors as they're turned toward different points of the sky. Pin-sharp pictures from the VLT. But for the very best observing, there's nowhere like the clarity of space. 1990 and the launch of the Hubble Space Telescope from the shuttle. Deployed by the shuttle's robot arm, astronauts gently place the telescope in Earth orbit. A $2 billion eye in the sky, 600 kilometers above the planet. Free of the atmosphere, Hubble is to have the sharpest view of the universe. It's to see 10 times finer detail than telescopes on Earth and to be 30 times more sensitive to light. That light is focused by 2 mirrors, then analyzed by 5 special instruments to the rear. But there's a problem. The center of the big mirror is too shallow. It means that light is arriving at 2 focal points instead of 1. Hubble's images are fuzzy, although computer correction helps sharpen them. From this to this. But despite the problem, there are triumphs. At the pivot of 2 galactic jets, Hubble identifies a massive black hole. The Andromeda Galaxy, and evidence that it once consumed another. Hubble discovers a double core. In the Whirlpool Galaxy, it spies a suspected black hole. And here, the remnant of a supernova. But Hubble needs a fix. December 1993, a shuttle crew suits up for the job. Hubble is grappled into the cargo bay. The first task is to replace the telescope's power supply, the solar arrays. They've caused a wobble. One array is furled for return to Earth. The other, which won't retract, is simply floated away. Hubble is designed to be serviced in space, but this is a major reconstruction. The new arrays look like rolled-up window blinds. They're secured to the telescope and unfurled. And now for the big fix. Riding the robot arm, this cosmic repairman opens the doors of the main instrument bay. Hubble is the size of a school bus, the instruments as big as telephone booths. Out here you can't forget your tools. A complete kit is mounted at the end of the arm. The objective is to install optics that correct the distortion of the main mirror. The least useful of Hubble's instruments, a light measuring device, is removed. It makes space for the corrective module. Next, the replacement of the camera that does 50% of Hubble's science. The astronauts work half the time by spotlight, for the telescope orbits Earth every 95 minutes. moving rapidly from light to dark. The new camera has its own built-in corrective optics, plus improved detectors. Thanks to the astronauts, the mission is a resounding success. An error, 1/50th the width of a human hair, is corrected. Hubble has 20/20 vision. For the Space Shuttle program, this is its finest hour. With new spectacles, Hubble fulfills its potential. The corrective optics work like a dream. Tiny mirrors, no bigger than a thumbnail, compensate for the distortion of the primary mirror. They bring incoming light to a perfect focus. Mars in exquisite detail. Even remote Neptune has features. But Hubble is best with deep space. Here, L-shaped images piece together the Orion Nebula, a vista of starbirth. These are clusters of hot young stars. And this, the debris of a supernova. Hubble's view of the Lagoon Nebula. And a galaxy in unprecedented detail. The Egg Nebula in ordinary light and infrared. One galaxy through two instruments, gas jetting from the core. Watch the power of Hubble as it penetrates a single spot in the sky, a region uncluttered by the stars of our galaxy or galaxies close by. Deeper and deeper. Finally, we're looking at some of the most distant galaxies ever seen, 4 billion times fainter than the limits of human vision. Hubble is unveiling the universe as never before. Color and light, but it's only part of the show. Visible light, the rainbow in the middle, is just part of a whole spectrum of radiation. It stretches from gamma rays at one end to radio waves at the other. That tiny band of visible light is the only radiation we see. All radiation is invisible. We see light because it reflects off particles in the atmosphere. The sun in ordinary visible light. Just a fraction of its radiation, but there are clues. Our bodies sense infrared as heat and ultraviolet as suntan. Like us, optical telescopes see only visible light. They miss the big picture. To catch the full spectrum of the universe, we need a different astronomy. It's awful. The orchestra's playing properly, but we are hearing just a small range of notes. That's how it is with the sky. Visible light is a note or two in the spectrum. We need the whole range, all radiation, to hear the full cosmic orchestra. Radio waves are the longest in the radiation spectrum. We catch them in dishes and bingo, we have pictures. A quasar, the core of a distant galaxy. An image in both visible light and radio. Take out the visible and radio reveals what it brings to the picture, especially the jet. An optical picture of the galaxy Centaurus A. Radio shows it's in turmoil, the aftermath of a galactic collision. A pulsar, a tiny superdense star spinning 30 times a second. With radio, we see its powerful radiation beams. Along the spectrum, from radio to infrared. Infrared can be gathered only in the driest places. Water vapor absorbs it. Arid mountaintops, or the wastes of Antarctica, are good. Water at the South Pole is well and truly frozen. To astronomers, infrared is important. It picks out warm cosmic dust. But like ultraviolet and the longest radio waves, relatively little penetrates our atmosphere. By and large, only visible light gets through. Most invisible radiation is absorbed by our atmospheric shield. To overcome the problem, detectors operate in Earth orbit. This is ISO, the Infrared Space Observatory. ISO must keep cool or be blinded by its own emissions. Anything hot radiates infrared. Veins of circulating liquid helium absorb heat and vent it from the craft. ISO is the coolest laboratory in the universe, minus 270 degrees Celsius. But infrared pictures are hot. Here in the constellation of Orion, infrared unveils vast clouds of gas and dust, a birthplace of stars. In ordinary light, the Large Magellanic Cloud, a galaxy very close to our own. In infrared, it displays great wafts of dust where stars are born. The Andromeda Galaxy in ordinary light, and here in changing wavelengths of infrared. By highlighting clouds of starbirth, infrared reveals Andromeda's spiral structure. Within our own galaxy, ISO gathers radiation from clouds between stars. Its long-wave spectrometer specializes in the job, imaging nebulae in the pangs of stellar birth. Still in infrared, but closer to home, ISO tracks a comet, its trail like condensation from a jet plane. In ordinary light, a comet's heart is obscured. But infrared gets through, and to the shells of dust that surround it. The composition of a comet, a fingerprint in infrared. In 1997, ISO divines water on comet Hale-Bopp. And when ISO peers toward our galactic center, there's water there too, in abundance, a medium for life. ISO, an eye on the invisible. By contrast, the Hubble Space Telescope is famous for the visible. But Hubble has peripheral vision too, infrared to one side, ultraviolet to the other. It's like stripping the veneer of a cosmic portrait. In ordinary light, a Hubble detail of the Orion Nebula. Pierce the dust with infrared, and Hubble uncovers cocoons of young stars. Again, in ordinary light, this Hubble picture hints at the next stop on the spectrum. The blue halo is from hot young stars radiating ultraviolet. The Andromeda Galaxy in ordinary light. But in ultraviolet, clouds of hot gas where massive stars die young. Halley's comet in ultraviolet, the dark blue a cloud of hydrogen enveloping the entire comet. Time-lapse of the sun, ultraviolet unmasking its churning surface. Shorten the wavelength to X-rays, and there are the hottest, most energetic regions, plus the corona, the searing atmosphere of the sun. The night sky as we see it, and as it is in X-rays. The orbiting observatory ROSAT targets the hot spots of the cosmos. It discovers 60,000 sources of X-rays. Like this galaxy with its turbulent core and very possibly a black hole. No doubt about galaxy M87 at the left. The neighboring blob is confirmation. It is material jetting from a black hole, better seen in this X-ray simulation. The remnant of a supernova, X-rays from the quivering entrails of an exploded star. Another, the Crab Nebula, with its pulsar, the relic of the star that exploded. It spins like a top, flashing like a lighthouse. In X-rays, here's the pulsar switched off. And here, switched on. It happens 30 times a second. X-rays reveal the sheer energy of the pulsar. It lights up the whole nebula. From Space Shuttle, the Compton Observatory is released into orbit. It detects gamma rays, the most energetic radiation of all. Compton finds it here, shooting from a supermassive black hole, jets of gas at 100 million degrees. And Compton charts gamma-ray bursters, mysterious blasts of energy. They seem to come from the farthest reaches of the cosmos. In gamma rays, a panorama of our galaxy, the Milky Way. The hot band across the center, cosmic rays colliding with interstellar gas. The Milky Way in X-rays. In infrared, showing lots of dust. In the wavelengths of radio. And in the radiation we know best, visible light. Just part of the cosmic orchestra, but nonetheless exquisite. Far from city lights and with just a whisper of cloud, the Milky Way straddles the sky. This delicate band of light is our home in the cosmos. For when we observe the Milky Way, we're looking sideways at a disk of stars. That disk is our galaxy, our island universe. From above, the Milky Way is a spiral, a family of some 150 billion stars. We belong to that family. Our sun is one of these stars. It lies 2/3 of the way from the galactic center. The Milky Way turns like a Catherine wheel, great arms spiraling outward. Within one of those arms, the sun orbits the galactic center once every 225 million years. Like a city, the center shines brightest of all. Veiled in gas and dust, it seethes with energy. But our neighborhood is suburban, quiet stars leading ordinary lives. The sun is no exception. It's yellow, average, and middle-aged. For an idea of scale, light from the Sun takes 8.5 minutes to reach Earth. Light from the nearest star takes 4.25 years to reach us. Astronomers call the distance 4.25 light years. The Milky Way is 100,000 light years across. From our position to the galactic center, it's 30,000 light years. The constellation of Orion rapidly loses shape as we hurtle through space. Stars that seem close together from Earth are really hundreds of light years apart. But in the vastness of our galaxy, we're still close to home. This group of young stars, the Pleiades, is 380 light years away. Closer are the Hyades, older, dimmer stars at 150 light years. And although from Earth it seems to be in the Hyades, this orange giant is less than half the distance. Aldebaran, over 100 times more luminous than the Sun. Sirius, the dog star, less than 9 light years, the brightest star in our night sky. Barnard's star, a red dwarf, 2,000 times dimmer than the Sun, and on its way toward the Sun. As it sweeps by in 10,000 years' time, it'll be our closest galactic companion. But for the time being, the nearest is Alpha Centauri, a trio of stars just 4.25 light years away. To see where stars are born, we must first look at another galaxy. This is M83, glowing pink in its spiral arms, regions of starbirth. In our own galaxy, these are such nurseries. They're called emission nebulae, clouds of glowing hydrogen streaked with black dust. Stars fire up where material clumps. Lower left, a brilliant young star in its dusty cocoon. And here, white-hot groups of new stars. The black dust in this nebula is scattered far and wide, dispersed by the winds of fierce new stars. Stellar birth is violent. Blowing together, an array of energetic infants clears this gigantic bubble in a red nebula. Young stars blow a hole 12 light years across at the heart of the Rosette Nebula. Australia is the starting point of this voyage into space. Travel is supposed to broaden the mind. This journey is to measure the cosmos, to set our position in the broadest context of all, the universe. We begin in Australia because it's good for observing the nearest galaxies. 2 mini-galaxies called the Magellanic Clouds. The small cloud is to the center, the large at the right. In the large cloud in 1987, a supernova blows. In fact, this supergiant expired 160,000 years ago. It's taken that long for the light of the flash to reach us. Andromeda is our closest major galaxy at over 2 million light years. At 10 million light years, the Silver Coin Galaxy, a spiral like Andromeda, and like our own galaxy, the Milky Way. We probably look like this. A spiral from above, the M83 galaxy, also at 10 million light years. We're now at twice the distance. The light of this galaxy takes 20 million years to reach us. This one, 35 million years. And from the beautiful Sombrero galaxy, 40 million years. Vast distances, but all these spirals are relatively close to us. This galaxy, Virgo A, is different. It's shaped like a basketball, an elliptical galaxy, one of a cluster up to 60 million light-years distant. The Virgo cluster is part of a supercluster of about 1,000 galaxies. Galaxies cluster because of mutual gravitational attraction. But how do we know this? How do we measure the cosmos or even the distance to our galactic center? Our galaxy is one of 30 in a local group. That group is part of a cluster, and the cluster part of a supercluster. Superclusters form strands across the universe. To help construct this model, astronomers use what they call standard candles. There's a standard candle in this galaxy, a pulsing star that brightens and fades as regular as clockwork. It's called a Cepheid variable, a star whose brightness varies as it expands and contracts. This one is big and bright and pulses slowly. But this Cepheid is smaller and dimmer and pulses faster. The speed of a Cepheid's pulse is directly related to its intrinsic brightness. So if we know the distance and true brightness of these nearby Cepheids, we can calculate the distance of remote Cepheids. Cepheids that appear fainter, but beat with the same pulse. In this way, we know that the Andromeda galaxy lies at a distance of 2.2 million light-years. Cepheids in our own galaxy are compared to fainter Cepheids here in Andromeda. But ground-based telescopes detect Cepheids only out to 15 million light-years. It takes the Hubble Space Telescope to see them in this galaxy at 55 million light-years. And in this galaxy at 80 million light-years. Beyond that, another sort of standard candle is necessary. Astronomers call it a Type 1 supernova. It occurs in a two-star binary system. A white dwarf, a star at the end of its life, swirls at the center of an accretion disk. It draws material from its partner. When the dwarf reaches the mass of 1.5 times our Sun, it explodes, a Type 1 supernova. The flash intensity is always the same. It's our new standard candle. From Cepheids, we know the distance of this galaxy. But because it also has Type 1 supernovae, that gives us the distance to our new standard candle. That candle, a Type 1 supernova, lets us measure up to 100 times deeper into space. But our journey has barely begun. In the 1920s, the American astronomer Edwin Hubble discovers our expanding universe, galaxies traveling outward in all directions. The evidence is in their light. As a galaxy speeds away, the lines of its spectrum move increasingly toward the red. The farther and faster a galaxy recedes, the greater the shift into red. The measurement of redshift is the greatest tool in the sizing and shaping of the cosmos. It suggests that the distance to the farthest reaches of the universe is 15 billion light-years. Mapping the heavens in the early 1960s, astronomers identify points of intense radio noise. Through optical telescopes, the sources appear as ordinary stars, but they can't be, for redshift puts them at billions of light-years distant. They're not radio galaxies. This one, Centaurus A, is noisy but less energetic. Nor are they Seyfert galaxies, radio sources that have brilliant cores. Seyferts are 100 times less energetic than radio galaxies and at least 10,000 times less than the new sources. But all three are fueled by supermassive black holes, voracious concentrations of gravity. The black holes in the new sources are gigantic, devouring the equivalent of up to 600 Earths a minute. For those radio astronomers have discovered quasars. Quasars are superluminous. They're the most energetic objects in the universe and among the oldest and the most distant, with enormous redshifts. Our sizing and shaping of the cosmos yields yet another great discovery: colliding galaxies. This is such a merger, the antennae galaxies. Simulated on computer, the two spirals don't really collide, but swing through each other like cosmic pendulums. Their gravitational interaction ejects two great tails, like the antennae of an insect. The merger triggers a starburst. New stars are born. The antennae are 63 million light-years away. At their center, a firestorm of star birth. This collision is like a spanner in the works. The intruder galaxy has passed right through the larger one, disrupting its structure. Here's a real picture of the same effect. It's the Cartwheel galaxy, scrambled as one of the small galaxies on the right ploughed through. In this collision, neither galaxy emerges. Instead, a supergalaxy is formed. In 10 billion years' time, that's possibly the fate of our own galaxy. We collide with Andromeda. We live in a mystery. It's called the universe. We can measure it, analyze it, observe it, even explore it. But what is the universe? How did it begin? Why did it begin? And how might it end? Some people reject the idea that it started with a Big Bang. Cosmologists generally accept the theory, but while they can explain how, they have no idea why. This is the theory of the Big Bang. From a single cataclysmic explosion, everything springs. From a speck smaller than an atom emerge matter, space, and time. It's blindingly hot. In the first microsecond, the universe expands to the size of a galaxy. It's a particle soup, growing bigger and bigger. It's so hot, energy spontaneously generates matter and antimatter. They annihilate each other and start again. Matter wins by 1 part in a billion. Matter is to dominate our universe. Protons, neutrons, electrons. The universe is now 1 second old. It's opaque, we can't see a thing. But physicists work it out. This expanding maelstrom seethes with subatomic particles. Atoms are about to form. At 3 minutes from the Big Bang, they create the first chemical elements: hydrogen, helium, and a trace of lithium. For 300,000 years, the cosmos is a fog. But as it expands, temperatures drop, our universe becomes transparent. For the first time, light and other radiation speed across space. A telescope can't show us the early universe. A particle accelerator can. This is an atom smasher. Electrified particles are crashed into each other at approaching the speed of light. For a split second, we're in the earliest universe. The collisions reproduce fleetingly the subatomic particles that abounded immediately after the Big Bang. The veil is lifting on the opaque universe. In 1965, Americans Robert Wilson and Arno Panzaius detect the first radiation of the visible universe. The horn behind them picks up a microwave hiss from every direction, an echo of the Big Bang at minus 270 degrees Celsius. As the universe has cooled, that signal, originally in ultraviolet, has shifted to microwave. It's called cosmic background radiation. This is COBE, the Cosmic Background Explorer. It makes sense of the microwave hiss. Like a super-sensitive thermometer, COBE takes the temperature of the universe, first removing the solar system. Then the Milky Way. What's left is an ancient temperature chart. From the first radiation of the visible universe, evidence that a primitive structure has emerged. That structure takes 1 billion years to develop. Ever expanding, galaxies in clusters, clusters on strands, the voids between growing wider and wider. Here, mutual gravitational attraction draws groups of galaxies into clusters, and clusters into superclusters. How galaxies form is a puzzle. We know how a supercluster like this evolves, but its collisions and mergers make it hard to unravel the earlier history of individual galaxies. Computer simulation confirms that the evolution of a supercluster is a violent affair. Some galaxies spin right out of the system. Gravity conducts a chaotic dance. It may last for billions of years. Young galaxies in the very early universe appear small and irregular, the product possibly of the repeated merger of smaller clumps. Those infant galaxies bear little resemblance to a mature spiral like this. Current thinking is that galaxies grow from smaller aggregations of matter in merger after merger. Subsequent development like this is better understood. Galactic interaction is the norm. Often it's cannibalism, big galaxies ingesting smaller ones. It continues to the present day. But what is the present day? How old is the universe? If it's expanding relatively slowly, we can deduce that the Big Bang happened some 15 billion years ago. If it's expanding rapidly, then the universe is younger, between 10 and 13 billion years old. Winding back to the Big Bang is one way. Another method of aging the universe is to look at stars hovering outside the plane of our galaxy. Such stars form groups of up to 1 million. Called globular clusters, they contain the most ancient stars in the universe. By analyzing their light, the age of these stars is initially set at up to 15 billion years, but the first windback results put the age of the universe at only 11 billion. These stars can't be older than the universe. The satellite Hipparcos helps resolve the issue. Its mission is to measure the distance of thousands of stars with unprecedented accuracy. Hipparcos employs parallax. It measures the shift of a foreground star against a more distant star. It does so from opposite positions in Earth's orbit of the Sun. The accuracy of Hipparcos is like measuring a golf ball on the Empire State Building from the other side of the world. Hipparcos proves that certain stars are 10% farther away than we thought, making the universe between 13 and 15 billion years old. Hipparcos finds that globular clusters are also farther away, making their stars younger, at between 12 and 13 billion years old. The older the universe, the slower it expands. So could it stop and reverse? Maybe, but one theory suggests the expansion of the universe will go on, till like a firework, momentum runs out. The universe will be dispersed, bleak and lonely. The theory of the Big Crunch is more dramatic. When expansion is exhausted, the universe teeters and reverses. It could only happen if there's enough matter in the universe. Matter creates gravity. Only gravity can orchestrate such a terminal crunch. There may be enough matter, for 90% of the universe is thought to be invisible. No one has ever seen a black hole, for nothing, not even light, escapes such gravity. Like black holes, 90% of the universe is invisible. Astronomers call it dark matter. This hidden mass is undetectable at any wavelength from gamma rays to radio. With 9/10 of the picture obscured, our ideas of the universe could be quite wrong. Dark matter may be largely responsible for the development and structure of the universe. The problem is, most of that structure is invisible. For all we know, the cosmos is made of monsters. Two stars orbit a common center of mass. They have a mutual gravitational attraction. We don't see the gravity, but we see its effects. The gravity of dark matter affects the rotation of this galaxy. Its spin is measured by the colors of the Doppler effect. Results show that outer parts of the galaxy spin much faster than its visible matter justifies. The cause is dark matter. Probably a hidden halo of up to 10 times the visible mass accelerates the galaxy. But dark matter shouldn't be confused with the dark clouds that pepper this galaxy. They're just visible dust. The matter we seek tugs invisibly on these stars. And it hints at a presence in these clusters of galaxies. Their interactions suggest up to 100 times more matter than we see. But what is dark matter? Is it dead stars, or failed stars, or black holes? Or is it exotic subatomic particles? This is the visible cosmos as we know it. The nature of dark matter and its part in shaping our universe remain two of the greatest mysteries in cosmology. A superstar draws matter from its smaller partner. The big star dies in a supernova, but the partner survives, still orbiting, still losing matter. For the superstar is now a black hole. In the real cosmos, we'd see the surviving star apparently orbiting an empty space. It's a clue used by astronomers to detect black holes. This is another. Although invisible itself, a black hole distorts light and space at its rim. Approach too close and you're spaghettified. A black hole is a collapsed star of such density, such gravity, that from within the rim, nothing escapes. To form a black hole, the core of the exploded star must be at least 3 times the mass of the Sun. But imagine Earth as a black hole. The mass of our planet is compressed to just 8 millimeters. It is so dense that light cannot escape and nothing travels faster than light. But light can be bent, and it helps us find dark matter. Here, light from a distant quasar travels to Earth. Put a big object in the way and our picture distorts. The object might be a galaxy with lots of dark matter and enormous gravitational pull. That gravity creates a crazy lens. It tugs on the light of the quasar, bending and multiplying its image. The picture we get on Earth is 4 images of the quasar with the lensing galaxy at the center. The degree of light bending reveals the amount of dark matter in the galaxy. When the lensing object is less symmetrical, it smears light. The blue arcs are far-off galaxies distorted by the cluster in the foreground. But the principle is the same. Gravitational lensing enables scientists to weigh dark matter. In the Milky Way, shrouded by the stars that crowd our galactic center, is a ring of gas. It has the mass of 30,000 suns. To many astronomers, such a swirl is evidence of only one thing: the pull of a massive black hole, a throat at our galactic center that has swallowed 1 million suns. Galactic collision is thought to spawn supermassive black holes. Like celestial dancers, 2 galaxies merge. A supermassive black hole is formed when the galactic cores unite. This is Centaurus A, the marriage of 2 galaxies, a white one shaped like a basketball and the dark one that we see edge on. At their single heart is a supermassive black hole. It has 1,000 times the mass of that hole in the Milky Way. And here's another, just as big. A supermassive black hole is surrounded by an accretion disk. Subject to irresistible gravity, matter swirls inward. Some matter jets at right angles to the disk, saved at the brink by the shock wave around the central vortex. Every hour, the equivalent of 4 Earths is consumed. This is an even bigger supermassive, a hole with the mass of 2.5 billion suns. It's at the center of the galaxy Virgo A. A great plume of material ejects across space. Here is Virgo A from the Hubble Space Telescope, the jet plainly visible. And this from a telescope on Earth. But the most incredible black holes are linked to quasars. Quasars burn at the center of remote galaxies, so fierce and bright that they outshine the galaxies themselves. Quasars are fueled by the hungriest black holes, supermassives that consume the equivalent of 600 Earths an hour. These are Hubble pictures. Quasars are among the most luminous and powerful objects in the universe. Albert Einstein, the great 20th century physicist, predicted many of the effects of supermassive objects. His general theory of relativity explains how bodies not only bend light, but distort the space around them. Our universe ripples with the push and pull of gravity, the exertions of supermassive objects. A black hole is the ultimate distorter. It so bends space and light that we've no idea what happens inside. It could be a wormhole to other parts of the cosmos, even to another universe.